Welcome to Breadboarding. In the previous video we managed to get some 44-pin surface mount chips soldered onto a breadboard adapter which could go directly into solderless breadboards. In this video I'm going to be looking at the 100-pin version. So these are 0.5mm spacing, they're so very small, and see if we can get one of these chips soldered on this 100-pin breadboard adapter and see if I can get that working. So this is part 8 of the Programmable Logic Devices, and this bit we're really looking at the complex Programmable Logic Devices, CPLDs, in particular the ATF1504 and the 100-pin TQFP surface mount chip. Okay, so here are the 100-pin ATF1504 and I've got over here a 100-way breadboard adapter. These things you can get off Amazon, and on one side it's got the 0.5mm 100-way one. You can see it will actually take chips from around 32 pins all the way up to 100. Then on the reverse side there's actually a 0.8mm 64-way one. So I'm going to try and solder this 100-way chip onto here. I'm not sure how successful it'll be. Now what I have just done is I've masked off the central bit here, because when I tin this, put flux and tin on this, I don't want it to go all the way down there, so I'm just going to try and pin the sort of last little bits of the pads there. So I'm going to try and do that now. If we just check what the chips are, you can see there hopefully ATF1504 10 AU100, so that means 10 nanoseconds and 100 pin. Okay, so I've masked off the central area there though, so we don't put too much solder over there, so just putting lots of flux on there. A little tiny bit of solder on the end of the tip of the iron, and then just run it over a couple of times. That should tin it quite nicely. You can never have too much flux on these things, it always seems to help smooth things along. So we'll just check it under the microscope. Now we're going to try and place the chip on in the right place. It always takes a bit of messing around to do this. You only have to sort of nudge something ever so slightly and it moves out the way. Try and then just tag one corner and then try and tag another corner, but it moved when I was doing that. So it just takes a little bit of messing around backwards and forwards to get all of the connections lined up. But once you have got it, then generally you can then just put flux over it and run the soldering iron with a little bit of solder on it over the connections, and it'll actually solder the leads in place. And then obviously if we have any bridge connections, we can then use the solder braid to actually clean up any of those. And in general, if we just put a bit more flux over it and run the soldering iron over it again, quite often it will help to tidy up some bits. I'm just going to clean it, and then we'll have another look at it on the microscope, and hopefully that should be sufficient. It's clean, so I'm just going to check on the microscope. I think there might be a couple of pins where the solder is bridging it, so I'll just have a look at that. So just checking all of the joints under the microscope here. So I'm just going to get a bit of flux with some braid and just heat up the solder there, and it will suck up the spare solder there. These ones here, some of them are not quite on the right there. Just try and resolder these, see if there's makes any difference. They're just going to cover it in more flux, actually run the soldering iron over it again. Just have to check those, so I'll go and clean that again. So then we'll wire up the dip pins, and then we'll check it with the meter to make sure the connections are okay. Okay, so that looked to be okay. I'm just going to check it one more time under the microscope, and then I'm going to start putting in the dip pins. So got 100 pins like this I need to connect. So I'm going to be putting 2 either side, which will plug into the breadboard, and then all the others are going to be pointing upwards, and then we'll use DuPont cables to wire in the rest of the board. Now I think I've sorted it. Some of these pins on the right hand side here which weren't quite attached properly, and I was able to very, very gently push some of them up onto the pads where they weren't quite aligned, and I have checked these now and they're all now in properly. So see down here, not all the pins are completely lined up with the pads for some reason, but I have checked that each of them is actually attached. And I will be doing continuity checks once I've got the 0.1 inch pins wired in. I wanted to make sure I could at least get some rows of pins plugging into the breadboard. So if I do a double power rail like this, then in fact this inner row of pins will line up almost. It's not 100%, but if the pins are in a slight angle, then what I'm going to do is to solder in these pins first of all, and then I've got a whole load of pins then put in from the other side, and those are going to be actually sticking up like this, and then I'll just be using DuPont cables to wire in the rest of those pins. Okay, so put lots of flux in there and just try and alternate the area of the board that we're putting this in, and then we're going to put all the other pins in now. Sometimes just put some of these 0.1 inch sockets on the back there just to hold the pins in place whilst I solder them in place there. Okay, so there we have it. To put it around the right way, we have a 100-pin surface mount dip adapter. So this is going to be quite fun to wire up and to label, but should be able to actually replace probably about half the logic on the CGA video card using one of these chips. And I'll probably use the other surface mount chip that I did in the previous video, and that will allow me probably to do most of the control logic in these surface mount chips. Okay, so now we need to wire this up. So I've made another JTAG connector, so this is just 10 dip pins, and I've got a slide from the previous video where we identified what the various pins on there were. So this is the printout from the data sheet. So we've got the 100 lead TQFP here. So these are all of the sort of global pins, the JTAG pins, where all the ground lines are, the VCC IO. So this chip can actually run at either 5 volts or 3.3 volts. Now the internal power supply for the internal chip needs to run at 5 volts, so those two pins must be at 5 volts. And these are the ones I'm going to run at 5 volts, but we could run these at 3.3 volts if we wanted to work with more modern chips like Raspberry Pis and things like that. And then the other key thing is all these not connected ones, these shouldn't be actually connected to anything else. We need to make sure we don't connect those. Then these pinout diagrams, this is the microcell number down the side here. So you've got from 1 to 64 in total, and then this is the 100-pin TQFP pin number. So we need to go through all of those, and then these ones as well. So all the way down to 64. Now, if you remember when we were looking at the 44-pin chip previously, then quite a number of these pins didn't have a external pin here, but we saw that we could use the feedback modes over here. We don't have to worry about it here because all of the macro cells actually have an external pin. So I've gone through all of that and come up with a sort of a diagram like this. So this, where there's a circle, that means it's not connected, and probably not that easy to see. But this was just really a sanity check to actually work out what was going on here. And you can see that there are chunks of not connected pins around the place. So when we're wiring things up, we may not need to go all the way to the end of the socket there in some cases. But we are going to need to make sure they wire in all the ground signals, all the VCC signals. We'll tie those all to 5 volts. And then the programming signals we need to worry about. So we've got the TDO there. We've got the TDI there. TMS there. And the TCK there. So those are the JTAG signals that we need to program this, so we're going to need to wire those up. That information is also being used to produce these PLDs. So this is a template PLD for the 100-pin version of the 1504. I'll come to the diagram in a minute. So we've got all of the JTAG pins that we need to avoid using, the global pins that we covered before, and now this time all the way down here, all of the microcell numbers here, rather than having some having pin node and some having pins, they all now have pins. So I've gone through all that and checked that all of those are correct. What I've also done is made sure that I've actually used things like the global clock, the output enable 1, output enable 2, and we'll see the reason for that in a minute. And also have done is just gone through and assigned all of the macrocell values have at least got something. So either it's on the right hand side or left hand side. And so all that means is that when we actually compile this and we get the fit output file from the fitter, what that means is all the pins are being used, and we can sort of see here, this is where it's placing floating pins, but because we've defined where all the pins are, we should see that MC1 goes to MC1 all the way down to 64, and obviously we've got our JTAG pins here as well, so it's identifying those. But the interesting thing is it also generates this 100 lead TQFP pinout. And what you'll notice here is, because I think I've included all of the microcells here and all of the global clocks and things like that, then in fact this pin layout is actually pretty accurate. And then further down here we've got the various multiplexers. Now what we might need to do is to use some of the automatic pin assignment if we run into problems with the fan in and fan out for the multiplexers and things at some point in time. But for the moment, I don't actually need to do that. And getting the layout to make it easy to wire up on the breadboard is probably going to be more important. And then we can see here all the nodes, and then there's also the pin table. And you can see where we're using some of the registers, clocks and things like that. There will be some of these extra terms used here for the first couple of macro cells, which have actually got the clocks and things on there. So what I've done is used this as a basis for doing our gate test that we had previously. So this was the original gate test that we had from early on in the series. And all this is doing is taking A and B and then producing these various outputs, logical outputs, using the rules here. And I did produce the same thing using the 44-pin version. You can see here they've got a couple of the outputs there, and we did test that in one of the EPROM programmers, the T56 programmer. We're able to actually test that this works. I'm not sure I'm going to be able to use that for this one because probably the pins aren't going to quite line up in quite the same way. So what I've now done is we've now got the equivalent of the gates version here. Now what I have done in this particular one is I've actually reordered the way how the pins appear here, so that it makes it easier to translate onto the breadboard adapter. So if we compare this one with the output from the other one, if you'll notice here, the even pins are on the inside, even on the inside. If we look at, you see here that the odd pins here on the inside, and because of the way how the breadboard adapter's made, then the even pins are on the inside. So all I've done is I've changed the layout here a little, and also the 76 is on the side here. I think 26 is on the side here, because you'll see here 76 is there and 26 there, because again that's the way how the pins are on the breadboard adapter. So hopefully this diagram will allow me to use this to mark up when I'm designing this, so that we can try and keep the inputs and outputs perhaps together. And I think what will probably happen is that the inside pins are actually connected into the breadboard, so all the even pins down here are actually connected to the breadboard, and all these other pins are going to have flying DuPont cables to plug into the breadboard. So this should mean that, at least from a labelling point of view, this will be something that we can work with. And the only thing we really need to do is, when the fit file is generated from here, we just need to be aware that the 76 and the 26 pins are just moved around on the diagram a little bit. This gates fit file shows that we've got the various logic rules in here. And so now what we need to do is to hook up the programmer to be able to program this, and then we should just be able to wire up a simple test. I'll probably just use the LEDs and the dip switches that I've got here just to run the test for this. And for programming this, I'm just going to be using one of the Atmel microchip USB programmers. The one I got off eBay just didn't have the case, but was about a third of the price. Now we just need to wire up the JTAG header on the breadboard. Now this is the slide from the previous video that we had for the 44-pin TQFP chip, and now I've just updated this for the 100-pin one. So you'll see now we've got the slightly different pins here, and we just need to remember to put the 10K pull-up resistors in here, otherwise it won't work. So I've wired this up, and I've actually done a little bit of testing. I had a few issues which I'll talk about as we go through, but what we'll look at now is just have a look at how it's been wired up. Okay, so it's quite busy. You can see down the bottom here we've got the Atmel programmer. So this is the JTAG output here going into the JTAG socket here. Got our two pull-up resistors here, 10K pull-up resistors. There you can see that some of the leads here, the white ones are the data ones, the TDO and the TDI I think are the white ones, and then the blue ones are the TCK and the TMS, and you'll see that the even pins are actually wired into the breadboard on the sides there, so that's just going through there, and this one is actually coming from the pins there. What I have done is made up my own cables. So I do have these sort of pins. So these are DuPont sort of cable sockets and pins. And if we use a crimping tool like this, you can make up your own cables, which is probably easier than breaking apart the ribbon cable. So I was able to make bits of cable that were exactly the right length. And what I needed to do is to go through and wire up all the ground, VCC, and make sure I wasn't joining anything I'm not connected. So you'll notice that we've got a lot of these cables here are the ground and 5-volt cables. And then I changed the pin layout a little to actually use the outputs for the various tests along here. Originally I thought I might have damaged some of the pins over here, but I think what it was, I'd forgotten to put the output enable. So this pin here, pin 8088, is OE1. At the moment it is active high, so I tied it to 5 volts. Generally output enables will be active low, and we'd put the reverse polarity on the pin definition, but I've just left this as a default that the Atmel chips come as, but I will probably change it to be active low going forwards. So the chip is wired up, we just need to program it, so I'll show you how to program this chip. So one of the problems I had when I was testing this is by default the Atmel devices have pin keeper enabled, and that does tend to make it a bit more difficult to see what the voltage on an output is because it has a weak sort of pull high or pull low. So I've disabled that. It took me a little bit of time to work out how to do this, although I knew what the property was here. For some reason in the original file I had it wasn't working, and you'll see there's quite a lot of files up here where I've tried this. What I ended up doing is there's a sample file pin keep PLD in the samples. I tried that and that worked, and in the end I found out that what the problem I think I had is that the file name was just a bit too long. When I renamed my file test.v2 and I put it in the samples folder, then in fact everything seemed to work okay. So what we've got here, similar to what I showed previously, but now rather than having the XNOR down to invert B pins down here, they're now down the bottom here, and this is all ready to be compiled, and all of the things have been recompiled here. So we're just going to copy that and go into WinCUPL. So just got that loaded already. Device dependent compile, and then the fitter will run in the background. So if we just have a look at the output file from that, and what we can see here, the pin keep mode is off, security mode is off, and I've also turned the slew rate or the output to be fast, so the chip can do transitions more slowly to avoid spikes and things like that. Because we're getting using this for video signals, then we really want things to be as fast as possible. We may need to make sure we've got a bit more decoupling. So the problem I was having is with the longer file name that I couldn't turn the pin keeper mode off. And that was meaning that the logic analyzer was having trouble actually picking up the signals. And I also needed to remember to put the output enable on. So output enables on pin 88. That is currently tied to 5 volts. So now it appears to be working. And you'll see that the diagram that it generates here has now got the various pin details down the bottom here. So now that we've got the GED file as well, and down the bottom here we'll see the special bits. Some of these bits down here are the bits needed to turn off the pin keeper, and that took a little while to get that sorted. Now to program this is what we did last time. We've got the ATM ISP. We just needed to load the chain file. We've only got one device in here, so if you just have a look at the details for it, you can see that it's the ATF1504. We're going to program and verify, and we're using our test v2.ged, and we'll try running that. Okay, so that's now finished. So what we need to do now is just to check the signals that we've got coming out of here. So if we go back to the testing here, we can see that we've got the A and B are the inputs going into pin 8 and pin 10. And then we've got these outputs, and the outputs have the following logic rules, which are the ones from the gates PLD from earlier videos. So this is very simple. Just going to include the inverted A and B, the AND of A and B, the NAND of A and B, OR of A and B, NOR of A and B, exclusive OR of A and B, and the exclusive NOR and A and B. So depending on the input values of A and B, we should see these various outputs change. And you can see here we've also got the output enable is using output enable 1, and that is set to 5 volts to true. So the logic analyzer is hooked up. You can see we've got the A and B pins there, and then the invert A, B, AND, NAND, OR, NOR, XOR, and exclusive NOR. Now because we've got this wired up to a dip switch which will produce the zeros and ones, so I'm just going to be doing this manually. So I'm going to run this at fairly slow 20 kilohertz. This will run for quite a number of seconds. So all we're going to do is to record this, and as I toggle the switches, hopefully we'll be able to see the values come out on here. So the switches are currently at 0 and 0, so I'm just going to run it now. Now we're doing bit 0 is now 1, back to 0. Oh, bit 1 is now 1, and then we'll put bit 0 at 1 as well. So now we have 3, and then we'll turn it back to 0. Back to 0 now. So we can now stop that. And we'll just add some markers. So first of all, we want the period when it's 0. So this period is 0. Then we've got the period when we've got 0, 1. So A is 1 and B is 0. Wider. Then we're going to have the period of time where we've got B is 1 and A is 0. Then we'll have the time when both the values are 1. And then finally, it'll all go back to 0 again. So if we have a look here, we can see that A is low, B is low, invert A high, invert B high, AND should be low, NAND should be high, OR will be low, NOR will be high, XOR will be low, because when the two values are the same, then you'll be low. When they're different, then it'll be high, and exclusive NOR will be high because it's the reverse of XOR. And we can see when we've got A is equal to 1, B is equal to 0, the inverse A is 0, inverse B is 1, AND is still 0, NAND is still 1, OR is now 1 because one of the inputs is 1, NOR is 0 now. Exclusive OR is 1 because the A and B are different, and the exclusive NOR has now gone to 0. Then we get over here, we've now just got the B is 1 and the A is 0. And again, the invert A is correct, invert B is correct, AND is now 0. NAND is still 1, OR is 1, NOR is 0. Exclusive OR is 1 because the two values are different, and exclusive NOR is 0. Then when we get to both values being 1, the A and B are 1, we've got the inverts are both 0. AND is now 1, NAND is 0, OR is 1, NOR is 0. Exclusive OR is 0 because they're the same. Exclusive NOR is 1. So that test appears to be working. So after the initial problems I had with programming it, in particular disabling the pin keeper circuit, then it looks that it's actually working okay. A number of people have made comments about the series here on the PLD, so thanks very much for the positive feedback. The only bit I've really got left now is once I've used one of these chips in anger, I'll hopefully find out a bit more about them and how to make use of them. I've only been using this for a very simple test at this point in time, but I'm going to be looking at using this particular chip for a lot of the output logic for the CGA video controller. So I should hopefully be able to replace many chips actually with this one PLD here. So that will be coming over the coming weeks. So if you don't want to miss out on future videos, please hit subscribe, and if you can hit like, just helps to make the videos available to more people. Thanks for watching.